of quantum physics on an ad hoc basis had left it without solid foundations or a logical structure. Out of this state of confusion and crisis emerged a bold new field known as quantum mechanics. The picture of the atom as a tiny solar system with electrons orbiting a nucleus, still taught in schools today, was abandoned and replaced with an atom that was impossible to visualize. Then, in 1927, Werner Heisenberg made a discovery that was so at odds with common sense that even he, the German wunderkind of quantum mechanics, initially struggled to grasp its significance. The uncertainty principle said that if you want to know the exact velocity of a particle, then you cannot know its exact location, and vice versa. No one knew how to interpret the equations of quantum mechanics, what the theory was saying about the nature of reality at the quantum level. Questions about cause and effect, or whether the moon exists when no one is looking at it, had been the preserve of philosophers since the time of Plato and Aristotle. But after the emergence of quantum mechanics, they were being discussed by the 20th century's greatest physicists. With all the basic components of quantum physics in place, the Fifth Solvay Conference opened a new chapter in the story of the quantum. For the debate that the conference sparked between Einstein and Bohr raised issues that continue to preoccupy many eminent physicists and philosophers to this day. What is the nature of reality? And what kind of description of reality should be regarded as meaningful? No more profound intellectual debate has ever been conducted, claimed the scientist and novelist C.P. Snow. It is a pity that the debate, because of its nature, can't be common currency. Of the two main protagonists, Einstein is a 20th century icon. He was once asked to stage his own 3-week show at the London Palladium. Women fainted in his presence. Young girls mobbed him in Geneva. Today, this sort of adulation is reserved for pop singers and movie stars. But in the aftermath of the First World War, Einstein became the first superstar of science when in 1919 the bending of light predicted by his theory of general relativity was confirmed. Little had changed when in January 1931, during a lecture tour of America, Einstein attended the premiere of Charlie Chaplin's movie City Limits in Los Angeles. A large crowd cheered wildly when they saw Chaplin and Einstein. "They cheer me because they all understand me," Chaplin told Einstein, "and they cheer you because no one understands you." Whereas the name Einstein is a byword for scientific genius, was and remains less well known. Yet to his contemporaries he was every inch the scientific giant. In 1923, Max Born, who played a pivotal part in the development of quantum mechanics, wrote that Bohr's influence on theoretical and experimental research of our time is greater than that of any other physicist. 40 years later, in 1963, Werner Heisenberg maintained that Bohr's influence on the physics and the physicists of our century was stronger than that of anyone else, even than that of Albert Einstein. When Einstein and Bohr first met in Berlin in 1920, each found an intellectual sparring partner who would, without bitterness or rancor, push and prod the other into refining and sharpening his thinking about the quantum. It is through them and some of those gathered at Solvay 1927 that we capture the pioneering years of quantum physics. It was a heroic time, recalled the American physicist Robert Oppenheimer, who was a student in the 1920s. It was a period of patient work in the laboratory, of crucial experiments and daring action, of many false starts and many untenable conjectures. It was a time of earnest correspondence and hurried conferences, of debate, criticism, and brilliant mathematical improvisation. For those who participated, it was a time of creation. But for Oppenheimer, the father of the atom bomb, there was terror as well as exaltation in their new insight. Without the quantum, the world we live in would be very different. Yet for most of the 20th century, accepted that quantum mechanics distance of beyond what was measured in their experiments. It was a state of affairs that led Prize Murray Gell-Mann to describe quantum that confusing discipline, which none of us really understands, but which we know how to use. And use it we have. Quantum mechanics drives and shapes the modern world by making possible everything from computers to washing machines, from mobile phones to nuclear weapons. The story of the quantum begins at the end of the 19th century when, despite the recent discoveries of the electron, X-rays, and radioactivity, and the on whether or not atoms existed, many physicists were confident that nothing major was left to uncover. The metallurgical science have all been discovered, and these are now so firmly established that the possibility of their ever being supplanted in consequence of new discoveries is exceedingly remote, said the American physicist Albert Michelson in 1899. Our future discoveries, he argued, must be looked for in the 6th place of decimals. Many shared Michelson's view of a physics of decimal places, believing that any unsolved problems represented little challenge to established physics and would sooner or later yield to time-honored theories and principles. James Clerk Maxwell, the 19th century's greatest theoretical physicist, had warned as early as 1871 against such complacency. This characteristic of modern experiments, that they consist principally of measurements, is so prominent that the opinion seems to have got abroad that in a few years all the great physical constants will have been approximately estimated, and that the only occupation which will be left to men of science will be to carry on these measurements to another place of decimals. Maxwell pointed out that the real reward for the labor of careful measurement was not greater accuracy, but the discovery of new fields of research and the development of new scientific ideas. The discovery of the quantum was the result of just such a labor of careful measurement. In the 1890s, some of Germany's leading physicists were obsessively pursuing a problem that had long vexed them. What was the relationship between the temperature, the range of colors, and the intensity of light emitted by a hot iron poker? It seemed a trivial problem compared to the mystery of X-rays and radioactivity that had physicists rushing to their laboratories and reaching for their notebooks. But for a nation forged only in 1871, the quest for the solution to the hot iron poker, or what became known as the black body problem, was intimately bound up with the need to give the German lighting industry a competitive edge against its British and American competitors. But try as they might, Germany's finest physicists could not solve it. In 1896, they thought they had, only to find within a few short years that new experimental data proved that they had not. It was Max Planck who solved the black body problem, at a cost. The price was the quantum. Part 1. The quantum. Briefly summarized, what I did can be described as simply an act of desperation. Max Planck. It was as if the ground had been pulled out from under one, with no firm foundation to be seen anywhere, upon which one could have built. Albert Einstein. For those who are not shocked when they first come across quantum theory cannot possibly have understood it. Niels Bohr. Chapter 1. The Reluctant Revolutionary. A new scientific truth does not triumph by convincing its opponents and making them see the light, but rather because its opponents eventually die, and a new generation grows up that is familiar with it, wrote Max Planck toward the end of his long life. Bordering on cliché, it could easily have served as his own scientific obituary, had he not, as an act of desperation, abandoned ideas that he had long held dear. Wearing his dark suit, starched white shirt, and black bow tie, Planck looked the archetypal late 19th century Prussian civil servant, but for the penetrating eyes under the huge dome of his bald head. In characteristic Mandarin fashion, he exercised extreme caution before committing himself on matters of science or anything else. "I'm always this," he once told a student. "Consider every step carefully in advance, but then, if you believe you can take responsibility for it, let nothing stop you." Planck was not a man to change his mind easily. His manner and appearance had hardly changed when, to students in the 1920s, as one recalled later, it seemed inconceivable that this was the man who had ushered in the revolution. The reluctant revolutionary could scarcely believe it himself. By his own admission, he was peacefully inclined and avoided all doubtful adventures. He confessed that he lacked the capacity to react quickly to intellectual stimulation. It often took him years to reconcile new ideas with his deep-rooted conservatism. Yet at the age of 42, it was Planck who unwittingly started the quantum revolution in December 1900, when he discovered the equation for the distribution of radiation emitted by a black body. All objects, if hot enough, radiate a mixture of heat and light, with the intensity and color changing with the temperature. The tip of an iron poker left in a fire will start to glow a faint, dull red. As its temperature rises, it becomes a cherry red, then a bright yellowish orange, and finally a bluish white. Once taken out of the fire, the poker cools down, running through this spectrum of colors backwards until it is no longer hot enough to emit any visible light. Even then, it still gives off an invisible glow of heat radiation. After a time, this too stops as the poker continues to cool and finally becomes cold enough to touch. It was the 23-year-old Isaac Newton who, in 1666, showed that a beam of white light was woven from different threads of colored light, and that passing it through a prism simply unpicked the 7 separate strands: red, orange, yellow, green, blue, indigo, and violet. Whether red and violet represented the limits of the light spectrum or just those of the human eye was answered in 1800. It was only then, with the advent of sufficiently sensitive and accurate mercury thermometers, that the astronomer William Herschel placed one in front of a spectrum of light and found that as he moved it across the bands of different colors from violet to red, the temperature rose. To his surprise, it continued to rise when he accidentally left the thermometer up to an inch past the region of red light. Herschel had detected what was called infrared radiation, light that was invisible to human eyes from the heat that it generated. In 1801, using the fact that silver nitrate darkens when exposed to light, Johann Ritter discovered invisible light at the other end of the spectrum beyond the violet: ultraviolet radiation. The fact that all heated objects emit light of the same color at the same temperature was well known to potters long before 1859, the year that Gustav Kirchhoff, a 34-year-old German physicist at Heidelberg University, started his theoretical investigations into the nature of this correlation. To help simplify his analysis, Kirchhoff developed the concept of a perfect absorber and emitter of radiation called a blackbody. His choice of name was apt. A body that was a perfect absorber would reflect no radiation and therefore appear black. However, as a perfect emitter, its appearance would be anything but black if its temperature was high enough for it to radiate at wavelengths from the visible part of the spectrum. Kirchhoff envisaged his imaginary black body as a simple hollow container with a tiny hole in one of its walls. Since any radiation, visible or invisible light entering the container does so through the hole, it is actually the hole that mimics a perfect absorber and acts like a blackbody. Once inside, the radiation is reflected back and forth between the walls of the cavity until it is completely absorbed. Imagining the outside of his blackbody to be insulated, Kirchhoff knew that if heated, only the interior surface of the walls would emit radiation that filled the cavity. At first, the walls, just like a hot iron poker, glow a deep cherry red, even though they still radiate predominantly in the infrared. Then, as the temperature climbs ever higher, the walls glow a bluish white as they radiate at wavelengths from across the spectrum from the far infrared to the ultraviolet. The whole acts as a perfect emitter, since any radiation that escapes through it will be a sample of all the wavelengths present inside the cavity at that temperature. Kirchhoff proved mathematically what potters had long observed in their kilns. Kirchhoff's law said that the range and intensity of the radiation inside the cavity did not depend on the material that a real black body could be made of, or on its shape and size, but only on its temperature. Kirchhoff had ingeniously reduced the problem of the hot iron poker. What was the exact relationship between the range and intensity of the colors it emitted at a certain temperature to how much energy is radiated by a black body at that temperature? The task that Kirchhoff set himself and his colleagues became known as the blackbody problem. Measure the spectral energy distribution of blackbody radiation, the amount of energy at each wavelength from the infrared to the ultraviolet at a given temperature, and derive a formula to reproduce the distribution at any temperature. Unable to go further theoretically without experiments with a real black body to guide him, Kirchhoff nevertheless pointed physicists in the right direction. He told them that the distribution being independent of the material from which a black body was made meant that the formula should contain only two variables: the temperature of the black body and the wavelength of the emitted radiation. Since light was thought to be a wave, any particular color and hue was distinguished from every other by its defining characteristic, its wavelength, the distance between two successive peaks or troughs of the wave. Inversely proportional to the wavelength is the frequency of the wave, the number of peaks or troughs that pass a fixed point in 1 second. The longer the wavelength, the lower the frequency, and vice versa. But there was also a different but equivalent way of measuring the frequency of a wave, the number of times it jiggled up and down, waved, per second. The technical obstacles in constructing a real black body and the precision instruments needed to detect and measure the radiation ensured that no significant progress was made for almost 40 years. It was in the 1880s when German companies tried to develop more efficient light bulbs and lamps than British rivals that measuring the black body spectrum and finding Kirchhoff's fabled equation became a priority. The incandescent light bulb was the latest in a series of inventions, including the arc lamp, dynamo, electric motor, and telegraphy, fueling the rapid expansion of the electrical industry. With each innovation, the need for a globally agreed set of units and standards of electrical measurement became increasingly urgent. 250 delegates from 22 countries gathered in Paris in 1881 for the first International Conference for the Determination of Electrical Units. Although the volt, amp, and other units were defined and named, no agreement was reached on a standard for luminosity, and it began to hamper the development of the most energy-efficient means of producing artificial light. As a perfect emitter at any given temperature, a black body emits the maximum amount of heat, infrared radiation. The black body spectrum would serve as a benchmark in calibrating and producing a bulb that emitted as much light as possible while keeping the heat it generated to a minimum. In the competition between nations presently waged so actively, the country that first sets foot on new paths and first develops them into established branches of industry has a decisive upper hand, wrote the industrialist and inventor of the electrical dynamo, Werner von Siemens. Determined to be first, in 1887, the German government founded the Physikalische Technische Reichsanstalt, PTR, the Imperial Institute of Physics and Technology. Located on the outskirts of Berlin in Charlottenburg, on land donated by Siemens, the PTR was conceived as an institute fit for an empire determined to challenge Britain and America. The construction of the entire complex lasted more than a decade, as the PTR became the best equipped and most expensive research facility in the world. Its mission was to give Germany the edge in the appliance of science by developing standards and testing new products. Among its list of priorities was to devise an internationally recognized unit of luminosity. The need to make a better light bulb was the driving force behind the PTR blackbody research program in the 1890s. It would lead to the accidental discovery of the quantum, as Planck turned out to be the right man in the right place at the right time. Max Carl Ernst Ludwig Planck was born in Kiel, then a part of Danish Holstein, on 23rd April 1858, into a family devoted to the service of church and state. Excellence in scholarship was almost his birthright. Both his paternal great-grandfather and grandfather had been distinguished theologians, while his father became professor of constitutional law at Munich University. Venerating the laws of God and man, these duty-bound men of probity were also steadfast and patriotic. Max was to be no exception. Planck attended the most renowned secondary school in Munich, the Maximilian Gymnasium. Always near the top of his class, but never first, he excelled through hard work and self-discipline. These were just the qualities demanded by an educational system with a curriculum founded on the retention of enormous quantities of factual knowledge through rote learning. A school report noted that, despite all his childishness, Planck at 10 already possessed a very clear, logical mind and promised to be something right. By the time he was 16, it was not Munich's famous taverns, but its opera houses and concert halls that attracted the young Planck. A talented pianist, he toyed with the idea of pursuing a career as a professional musician. Unsure, he sought advice and was bluntly told, "If you have to ask, you'd better study something else." In October 1874, aged 16, Planck enrolled at Munich University and opted to study physics because of a burgeoning desire to understand the workings of nature. In contrast to the near militaristic regime of the gymnasiums, German universities allowed their students almost total freedom. With hardly any academic supervision and no fixed requirements, it was a system that enabled students to move from one university to another, taking courses as they pleased. Sooner or later, those wishing to pursue an academic career took the courses by the preeminent professors at the most prestigious universities. After 3 years at Munich, where he was told, "It is hardly worth entering physics anymore because there was nothing important left to discover," Planck moved to the leading university in the German-speaking world, Berlin.
I might have it myself.
With the creation of a unified Germany in the wake of the Prussian-led victory over France in the War of 1870 to 1871, Berlin became the capital of a mighty new European nation. Situated at the confluence of the Havel and the Spree rivers, French war reparations allowed its rapid redevelopment as it sought to make itself the equal of London and Paris. A population of 865,000 in 1870.